Now we've defined what it means for a function to be continuous at a point. Now we're going to extend that to the concept of continuous on an open interval. A function is said to be continuous on an open interval, we'll call that interval I, if it is continuous at every point within that interval. Now what that means is that as long as the function has limits that exist and function values that match the limit, that is to say, if we're allowed to use the direct substitution property on it, then we're going to be okay as far as continuity on that interval is concerned. So what I'd like to do is determine all discontinuities of the following function, f. So f is defined piecewise. F of x is going to be negative x minus 4 as long as x is less than or equal to negative 1. It's going to be x squared minus 4 as long as x is greater than negative 1 but less than or equal to 2. And it's going to be 3x minus 2 as long as x is greater than 2. So the first thing I'll have everybody take a note of is that the domain is going to be all real numbers. And the reason that I can surmise that is because if I take all of the intervals of the domain that are listed here, the first one says less than or equal to negative 1. The next one says greater than negative 1 but less than or equal to 2. So that takes care of all of that. And then the last domain says everything greater than 2. So the domain is going to be all real numbers. Now on the individual intervals, making use of the direct substitution property is going to be okay because all of these are polynomial functions, either linear or quadratic, depending on whether you see just an x or whether you see an x squared. So the definition of continuity is going to come into play wherever there is a change in the definition of the function. So what we need to do is check for continuity at x equals negative 1 and x equals positive 2. Specifically, because there are breaks there in the definition of the function, what we're going to do is compare a left-hand limit with a right-hand limit. So the limit as x approaches negative 1 of f of x, we're going to check to see whether or not that matches from the left and from the right. So from the left up here and from the right down here. Now when we say negative 1 from the left, we're referring to values that are less than negative 1. So this would be saying take the limit as x approaches negative 1 from the left of the rule that we use for x being less than negative 1. So that'll be negative x minus 4. In this form, we can use the direct substitution property to say that this would be negative 1 minus 4, or 1 minus 4, which is negative 3. Whereas when we approach from the right-hand side, we would be talking about values of negative 1 that are greater than negative 1. So we'll be using the second rule for that. So this will be the limit as x approaches negative 1 from the right-hand side of x squared minus 4. Once again, we can use the direct substitution property for this and plug in negative 1 for x. We square the negative 1, we get positive 1, we subtract 4, and we get negative 3. What this means is that the left-hand limit and the right-hand limit are equal to each other. Moreover, the definition of the function f of negative 1 would be equal to this negative 3 as well. Therefore, the function is continuous at x equals negative 1. Therefore, f is continuous at x equals negative 1. Now we'll be doing the same thing for x equals 2 since there is a change in the definition of the function there as well. So for x equals 2, once again we'll be checking the limit as x approaches 2 from the left side and the limit as x approaches 2 from the right side. Now from the left side means that we're going to be using the definition of the function for where x is less than 2. So less than 2 would be the middle definition of the function, so that'll be x squared minus 4. For that we can use the direct substitution property and say that this is equal to 2 squared minus 4. 2 squared minus 4 would be equal to 0. When we approach x equals 2 from the right-hand side, From the right-hand side means that x is greater than 2. X is greater than 2 uses this rule for the function. So this will be 3x minus 2. If I apply the direct substitution property to this, that would be 3 times 2 minus 2, which is equal to 4. You'll note now that the left-hand limit and the right-hand limit are not equal to each other. Therefore, the limit as x approaches 2 as a two-sided limit does not exist. Therefore, f has a discontinuity at x equals positive 2. And if we had to classify what kind of discontinuity it is, that would be a jump discontinuity due to the fact that the limits are not equal to each other, the left-hand and right-hand limit. If we were to sort of eyeball a sketch for what this thing looks like, here's negative 1, here's positive 2, then we would have a closed circle at negative 3, where these two things hit each other, so negative 1, negative 3. To the left, we'd have a slope of negative 1, and to the right, we would have a portion of a parabola up until we get right here. Now, please note that the parabola is going to have the closed dot at 2, and that the straight line would have an open circle at 2, 4. 1, 2, 3, 4. So open circle up here, and then it would have a nice positive slope after that. Wouldn't necessarily hit the y right in the tail, but in my picture it does. So that's where we see our jump discontinuity, and here's where we see that the function does retain its continuity.